We've looked at a few different types of reactions so far, one of which is a metathesis reaction, which involves the formation of a precipitate or an insoluble salt. Another type of reaction we've looked at is a neutralization reaction, in which case the product is the formation of water. We're going to look at a different kind of reaction now called oxidation reduction reactions or redox reactions. And a couple of examples of redox reactions would be, first of all, combustion reaction, which involves the production of energy, among other things, and also cellular respiration, in which the food that you eat is broken down and used as energy. If you cut an apple and let it sit out on the counter for a little while, it starts to turn brown. What's actually happening is a reaction with the oxygen that's in the air. This is the old school definition of oxidation, which was anytime a substance reacts with oxygen or combines with oxygen from the air. Now we have a more updated definition of what oxidation is. We've expanded the definition of oxidation to mean the process of an atom losing an electron. And this can only happen if there's an atom prepared to take that electron or undergo reduction. You can't have one without the other. Now, atoms that have only one or two valence electrons are going to pretty easily undergo oxidation, because if they can give up that valence electron, that will give them now a complete valence of 8. And an atom that only needs one or two electrons to complete its octet then will very easily accept that electron and undergo reduction. Now this can all get pretty confusing, so the way I remember this is Leo the lion says grr. Loss of electrons is oxidation, and gain of electrons is reduction. Since redox reactions involve the transfer of electrons, it's important that we keep track of where those electrons are being transferred from and to, and how many electrons are involved. And so we use a process of assigning oxidation numbers to help us keep track of those electrons. Now, when we are writing the charge of an ion, we would typically write it as, for example, in the case of magnesium ion, we would write Mg 2+. If we're writing an oxidation number, we would write it as a +2. So just note the distinction there. The first rule for assigning oxidation numbers is that uncombined elements are 0. So the oxidation number of, for example, molecules of oxygen or hydrogen or sulfur molecules would all have an oxidation number of 0. They're pure uncombined elements, not bonded to anything else. The second rule, if we're talking about an ion, the oxidation number will be the same as its charge. Rule number 3, oxygen is always going to be an oxidation number of -2, unless it's a peroxide, in which case it would be -1. And hydrogen is always a +1 as long as it's bonded to a nonmetal. In the case of a metal hydride, or hydrogen bonded to a metal, the oxidation number in that case for hydrogen would be a -1. And in a neutral compound, the sum of the oxidation numbers should all equal 0. So in the case of water, since oxygen's oxidation number is always -2, except in peroxides, then we would assign an oxidation number here of -2 to the oxygen. And hydrogen has a rule that it's always +1 when it's bonded to a nonmetal, which oxygen is, so hydrogen should be a +1. And the sum of those oxidation numbers should add up to 0, because this is a neutral compound. So we have 2 hydrogens, each with a +1, giving the hydrogen side a +2, and 1 oxygen with a -2 oxidation number equals 0. In the case of sodium sulfate, sodium being an ion would also have an oxidation number of +1. We also know that there's a rule for oxygen. Oxygen's always a -2. Now there's no rule for the sulfur, so we're going to have to determine, knowing that the sum of those oxidation numbers will add up to 0, we're going to have to determine what the oxidation number for the sulfur is. So there are 4 oxygens, each with a -2. That gives us a -8. And we have 2 sodiums, each with a +1. That gives us a +1. So +2 plus 6 minus 8 would give me a 0. So the oxidation number for the sulfur in this instance would be a +6. Now for sodium sulfite, let's apply these rules once again. The sodium, since it's an ion, is going to have an oxidation number the same as its charge, which is a +1. The oxygen has a rule that it's always a -2, so we'll go ahead and assign that. We know the sum of the oxidation numbers has to be 0, and so we will determine what the sulfur is going to have an oxidation number of. Since we have 3 oxygens, each with a -2, that'll give us a -6 for the oxygen portion. We have 2 sodiums, each with a +1. That gives us a +2 on the sodium, so we have a +2. That means the sulfur must be a +4 oxidation number to give us a sum of 0 for the entire compound. Many metals can be oxidized by acids or salts. And this is an example of a redox reaction between zinc and hydrochloric acid. This is a type of a displacement reaction, since one of the ions in solution is going to be displaced. Now I could determine that this was indeed a redox reaction just by taking a look at all of the oxidation numbers of all of the species present in this equation and determining which of those species has undergone a change in its oxidation state. So I have zinc, which is an uncombined element, so that's going to have an oxidation number of 0. Then we have HCl, and I know that the oxidation number for hydrogen is always +1 as long as it's bonded to a nonmetal. And so chlorine then would have an oxidation number of a -1, since that's a neutral compound and the oxidation numbers have to add up to 0. So moving over here to my zinc chloride, zinc being an ion in this solution would have an oxidation number based on the 2 chlorines, also ions of +2. The chlorine would be a -1. And the hydrogen is an uncombined element, once again, with an oxidation number of 0. So if we look from one side of the equation, the reactant side, to the product side, we can see that our zinc starts out with an oxidation number of 0. And on the reactant side, it ends up with an oxidation number of +2. Our hydrogen on the reactant side has an oxidation number of +1, and on the product side, hydrogen has an oxidation number of 0. And then the chlorine, or the chloride ion, has an oxidation number of -1 on the reactant side, as well as the product side. So the chloride ions, the chlorine actually did not take place in this redox reaction. The reaction happened between the zinc and the hydrogen, since that's where we see a change in the oxidation state. So the next step in this process is going to pull out half reactions showing what happened particularly to each species. First, let's take a look at what happened with the zinc. So we started out with zinc with an oxidation number of 0 on the reactant side, and then on the product side we have ZnCl2. Now we said that this is an ionic compound, and a chloride ion would have a -1 charge, and the zinc in this case would have a +2 charge based on the fact that it is bonded to 2 chlorides, each with a -1. It's the zinc that we're particularly interested in, though, because the chloride didn't actually take place in the process. So the zinc went from an oxidation number of 0 to plus 2. So it got more positive. And since electrons have a negative charge attached to them, and the zinc in this case is getting more positive, then it must have lost 2 electrons. So we're going to write that, since it's losing those electrons, as being lost on the product side. And we know Leo of Alliance is Gur, so a loss of electrons then means that this is our oxidation process. So zinc has undergone oxidation here. Now we'll take a look at our other half reaction that's involved here, and that is going to be involving the hydrogen. So we have 2 HCl, and on the product side we have H2 gas. And we started with an oxidation number of the hydrogen as a +1 on the reactant side and as a 0 on the product side. So note that we do have 2 hydrogens on each side. We do need to take into account, make sure that we are balanced for the correct number of atoms there. So each hydrogen went from +1 to 0. And so became more negative. And since electrons have a negative charge attached to them, we can assume then that the hydrogen gained those electrons. So each hydrogen went from a +1 to a 0. I have 2 hydrogens on both sides, and so that's going to be a net of 2 electrons that were gained by the hydrogen. And since hydrogen gained electrons, we know that gain of electrons is reduction. So our hydrogen underwent reduction in this process. Some metals are pretty unreactive. For example, gold and platinum and silver are really pretty unreactive, which is why we use them to make jewelry. So how do we know whether or not a metal is going to react in an acid or a salt? We can use the activity series. Any metal on the list can be oxidized by the ions of the elements that are below it. So, for example, potassium up here at the top of the list with 1 valence electron can be oxidized by sodium or calcium or magnesium or aluminum. But down here at the bottom of the list we have gold and silver. Platinum would be down here too, are pretty unreactive, and so there's not much below gold here that would oxidize it. And so this is an introduction to oxidation-reduction reactions, and we will delve into it a whole lot further in a future chapter.